Right, good evening everybody.
Evening.
This is a short talk called Ancient Light, and as you can see from the subtitle, it's about imaging a quasar without using a telescope. So it starts with a lockdown challenge because, as you don't need to be told, 2020 was a rather unusual year in which life as we knew it changed completely, and we ended up with a life in lockdown. So this object on the left gave rise to a lot of these objects on the right. Pretty much everywhere you went, whether it be paving slabs on the street or in offices or in supermarkets, you look down and you see footprints. But whenever I saw these, I thought to myself of the words of Stephen Hawking, who said, "Remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist." So I thought, yeah, okay, let's do that. Let's not look down at our feet. Let's look up into the sky and just how far can you see? A friend of mine in Bromsgrove Astro said once that he had imaged a very distant quasar with his telescope. And that got me thinking, well, if we're looking up and we're trying to find a very distant object, how far can you go? What sort of distance can you reach without using a telescope? So that is the challenge that I set myself effectively. We all know that the universe is vast and the universe is ancient. And we know that large telescopes have imaged galaxies that are billions of light years distant. But the question is it possible to capture an image of one of these very remote objects without using a telescope? And spoiler alert, yes it is. Otherwise this would be an even shorter talk and a very disappointing one. Okay, so where did we start? Well, I looked at a publication here in the Astrophysical Journal of people who had done a survey of quasars. And a quasar is the nucleus of a galaxy that emits so much light that these quasars can be observed from billions of light years distance. So what they actually look like, well, arguably we don't really know what they look like because they're so distant we can't actually get any detail. But we are pretty sure that the central engine that's producing all the light to make these quasars visible over immense distances, the central engine is almost certainly a supermassive black hole. So right at the heart of the galaxy, a so-called active galactic nucleus, a supermassive black hole feeding on lots of matter that's falling into the black hole, and on the way in, before it reaches the event horizon, the material gets very hot and radiates across the entire electromagnetic spectrum. So that's what we think a quasar actually is. So coming back to this survey, I looked at what they had deduced about various quasars that exist in the sky, and I found one in particular that was very distant and was visible high in the sky from the UK. This was last year, the middle of last year, so I wanted it to be visible high in the sky during the summer months. And I found this particular object. This is the spectrum of the object. You can see here from blue to red in units of angstroms, 10 to the minus 10 meters, from 4,000 in the blue to about 7,000 in the red. And the spectrum is a very valuable way of determining what you're looking at, and in particular for these distant quasars, how fast they are receding from us. If you remember the Hubble law, the further an object is away, the more rapidly it is receding from us. And so by measuring how much the spectrum has shifted towards the red end of the spectrum, that tells us how fast the object is moving because of the effect called the Doppler effect. The bigger the shift of the spectrum towards the red, the faster the object is receding from us. So I didn't recognize what was in this spectrum, but I'm told by the people that analyzed this that that particular peak, which occurs, we can see it's measured at a wavelength of about 6,500 angstroms, I am reliably informed that that actually should be in the ultraviolet part of the spectrum, way off to the left-hand side of the spectrum. So that belongs, if you like, at 1200 angstroms. That's where that peak would appear if the object was not receding from us. In other words, if we take a similar spectrum but from a laboratory-based source, that peak would occur at 1200 angstroms. But it's been shifted all the way from 1200 to 6500 because of the extreme velocity at which this object is receding from us, because of its great distance. And the amount of the shift, the redshift, is quantified by looking at how much it shifted compared to where it originally was. So if it was originally at 1200 and it shifted to 6500, that means it's shifted by, what's that? The difference is 5300 angstroms. And so the redshift is the amount it's shifted, 5300, divided by the original number. So what's 5300 divided by 1200? Well, they did the maths and they figured that it came out with a redshift of 4.3 and change. And a redshift of 4.3 means that this object is very remote. We'll come back to the actual distances in just a little while, but suffice to say that when I saw this in the survey with such a large redshift and being well to the north and visible from the UK, almost overhead as far as we're concerned in the UK during the summer months, that was an ideal target to go for. I didn't want anything that was too low down and either lost in the murk or lost behind a neighbour's house or something like that. So that's how I decided on this particular object. I then took my trusty camera, so it's not a modified camera, not a special camera, it's a Nikon camera with a telephoto lens. You can see it here. It looks a little bit longer in that picture simply because it's got a lens hood on the end there. But this is the same camera I use for day-to-day photography. In that sense, nothing special about it. It happens to be a Nikon D7500 digital SLR. And my favourite lens of choice is a 300mm f4 lens. And you can see I've mounted that on top of this white box, which is a star tracker, or this particular one is an Ioptron sky tracker. Other trackers are available. They are simply motorised boxes which turn at 1 revolution per day. So providing you line them up with the Earth's axis, they will effectively derotate the Earth. So as the sky moves, so the camera should track the sky, because as the Earth is turning, this will be turning in the opposite direction at the same rate, and so the camera ought to stay pointing at the same star. So that's all it is a motorised box with a few batteries in it and a motor that will track at 1 revolution per day. As I say, there are a number of different designs of commercial trackers available, or indeed you could build one for yourself if you so wish. So that's what I set up outside my front door, trying to avoid any streetlights shining into the lens, and I pointed it at a particular patch of sky. Let me just reiterate that this is not a special camera, this is just the camera that I normally use, this SLR camera and lens. These are what I use for wildlife photography, one of my other hobbies. They're not modified, it's not specialised, it's not customised for astrophotography. So in a sense, the question I'm asking is, can we take a camera like that that's designed to be used to photograph zebras or other daylight objects, can we take that particular combination of camera and lens and expect it to capture the light from a very remote object? Is it good enough for zebras? Is it good enough for quasars? So, which part of sky did I look at? Well, I checked the survey that said the coordinates of this particular quasar, and I looked them up and it happened to be in the constellation of Draco, quite close to overhead at the middle of the year. That little orange rectangle there, you can see, shows the field of view of the 300mm lens. And you can see here's Polaris and here's Ursa Minor. Now, there happens to be a little dot, perhaps you can see it in the middle of the rectangle. That's not the quasar is very faint, remember. That happens to be a 5th magnitude star, which fortuitously is quite close to the quasar. So that actually gave me something to look at when I was outside in the dark trying to point the camera in the right direction. It was quite fortunate that once I'd realised that I was pointing at that particular star, I knew the quasar was close by. So I focused very roughly on that star, got it approximately in focus, and then found a slightly fainter star somewhere else in the field of view, and I ended up focusing on an 8th magnitude star, which is faint enough to give you a very accurate focus. If a star is too bright, it's very difficult to tell when you've got the star focused down to a point. A fainter star, it's a little easier to see when you've got the focus spot on. So I checked the focus, made sure I was pointing in the right direction, and then set off a few exposures. I wanted to expose for as long as possible. This was taken in July, not that long after the solstice, so the night was actually quite short. There was only 2 to 2.5 hours between the end of evening twilight and the start of dawn twilight. So I didn't have very long, and I wanted to take essentially as long as exposure as possible. I wasn't sure just how faint this particular quasar was going to be and how long I'd have to expose for, so I just wanted to take as long as exposure as possible. And of course I didn't decide to take one long 2-hour exposure. I took a series of shorter exposures. I found that 30 seconds was fine, and I simply set the camera to keep taking 30-second exposures for as long as possible until it looked like the sky was starting to lighten slightly. There were some clouds going by, and one advantage of taking a lot of short exposures is that if a few clouds scud by, you don't have to stop an exposure, you just carry on taking images, and when you're done you've got a few hundred images, some of which have been spoilt by satellites or aircraft or clouds scudding by, and you can simply throw those away and add up all the remaining images. So this is the result of adding up more than 200 individual images, each of which was about 30 seconds long, giving me a total exposure around about 2 hours. And I knew that the quasar ought to be in that square there, knowing by looking at a star atlas and checking the coordinates of where the quasar is compared to the coordinates of that bright star in the middle of the field of view. So I zoomed into that to see whether I'd caught this quasar or not. And there it is, as indicated by the red lines. That is the quasar I was trying to capture. So most of the light from this very distant quasar is focused into barely more than 1 pixel. If we blow that up still further, we find that most of the light has gone into that 1 central pixel. Some of the light might have gone into the neighbouring pixels. In this particular inset, I've brightened the image to make these other pixels a little bit brighter so you can see them a little more clearly. But in fact, most of the light has gone into that single central pixel. So although the camera has got a 20 megapixel sensor, only one of those pixels was actually picking up the light from the quasar, or essentially just one of the pixels was picking up the light from the quasar. Just as an aside, what sort of resolution could we expect from the lens and the camera? Well, the lens has a particular aperture, about 75 millimeters in this particular case, and so you can work out from the laws of physics the limit, the so-called diffraction limit, that tells you what the resolution could be in the absence of any particular aberrations of the lens. This particular lens is quite a nice, good quality one, so I don't expect there to be any serious aberrations. And given a 75 millimeter aperture, you might expect to get a resolution of about 9 microradians, millionths of a radian. Physicists prefer radians, astronomers tend to prefer arc seconds. So 9 microradians is a little bit less than 2 arc seconds. And if we work out how big the pixels are in the sensor of the camera, that works out to be about 3 arc seconds. So reasonably well matched. I would guess that the seeing conditions would be of order a couple of arc seconds, so the seeing, which will probably limit the resolution, and the quality of the lens and the size of the pixels are all in the same neighbourhood of around about 2 or 3 arc seconds, so they're reasonably well matched. And just to give an idea of scale, if we're talking about an object which is billions of light years away, then if we ask how big would the Milky Way appear if it was at that distance, well, I calculated that the size of the Milky Way would be of order a couple of pixels or so. In other words, the Milky Way would have a diameter of about 6 arc seconds. So with each pixel being 3 arc seconds, I reckon the Milky Way would, if it was visible, have a size of a couple of pixels or so. That just gives you an idea of the sort of scale we're talking about. Whilst I was looking at that, although I was very satisfied with the fact that the quasar was quite easily visible and the signal to noise was quite good, there wasn't too much noise in the background, so the quasar stood out very nicely against the background. Perhaps I could have taken less than 2 hours. I haven't yet checked, but I might go back and take only a fraction of the images over the 2-hour period, maybe take half of them or a quarter of them and try adding them together and see if the quasar is still clearly visible. That would tell me that perhaps 2 hours was a little bit of overkill and I could have got away rather less. Maybe I'll try again next year with much shorter exposures. But whilst I had this particular crop, that particular crop of the whole image is only about 8 arc minutes by 8 arc minutes in size. And by checking it against the Sloan Digital Sky Survey, I realised that I'd actually caught a few galaxies in there, as well as a few foreground stars. Now, I don't expect you to see the content of those red circles as galaxies, but perhaps you can just about make out that some of these are a little bit extended. They're not quite circular. That's a little bit elliptical. That's a little bit distorted. But some of these fainter ones, you really can't tell that they are galaxies rather than stars. I had to rely on comparisons with a professional survey. But on realising that I'd caught something of order 10 galaxies in addition to the quasar, and that was in an 8 by 8 arc minute crop of the entire image, if I assume that that's representative of the whole image, and there's no reason to assume why it wouldn't be, that would mean that I've probably caught about 7,000 galaxies in the entire image. And it's sobering to realise that in this particular deep field, which I've rather modestly called the BADAS deep field, I think I might have caught 7,000 galaxies, which is comparable, roughly speaking, to the number of galaxies caught in the Hubble deep field. I'm not claiming this is as good, but it's interesting to know that you get a similar number of dots in your image at the end of the day. So let's return to the gritty question of what's the distance then? I've said that this is a very remote object. I've said that this object has a redshift of over 4, which tells us it's very remote. So what's the distance? Part of the problem is when you talk about the distance, you have to be very careful about what you actually mean. Remember, it's very remote, so the light left this object a long time ago. So we can imagine the distance between the Earth and the galaxy when the light left the galaxy. In other words, the distance then. And we can say, what was that distance? Indeed. But of course, the light has then been travelling for a long time on its way from the galaxy to Earth, and during that time the galaxy has been moving because space continues to expand, the universe continues to expand, and the galaxy is along for the ride, so the galaxy is moving away from the Earth, and the light is travelling through space, which is also trying to expand. So the light is moving through space and the space is expanding as it goes. And finally, the light arrives at Earth and enters the camera, and of course the galaxy has moved still further. So when you talk about the distance, what do you mean by the distance? Do you mean the distance when the light left? That's how far the galaxy was from Earth. Or do you mean how far is it from Earth now? Or do you mean how far has the light travelled? Because that is a different distance again. The light has travelled during the time the light has travelled, space has expanded. So actually, when you're thinking about that particular distance, that is a rather tricky thing to work out in its own right, simply because you're not dealing with something that is static. The galaxy has gone flying off. The photon of light, the light that left the galaxy and is on its way to Earth, doesn't know what the galaxy is doing. It is simply moving through space at the speed of light. But if space is expanding, then, well, it's a bit like a swimmer swimming through water and the water is moving Just like a swimmer swimming against the tide, the swimmer might be swimming at a particular speed through the water, but if the water itself is moving, then of course that will affect how long it takes the swimmer to get to the shoreline. Another analogy you can use when you're thinking about the light travelling through space from the galaxy to Earth is to think of it in terms of, imagine an ant is walking along a rubber band. If the rubber band is static, then you just measure the speed of the ant and you can work out how long it will take the ant to get from A to B. But if the ant is moving along a rubber band and while it is moving you are stretching the rubber band, then it's altogether more difficult to work out how long it takes the ant to get from there to there. So how are we going to actually work that out? How are we going to work out how long it takes the light to get from this distant object to us? Well, the only way of doing it is to work out using a model of how we think the universe has been expanding. If we have got an understanding of, well, the universe started off this size and has been expanding like this, then we can work out, well, if it's expanding in a particular way, then if the light left at that point and then arrived at this point, we can work out what space was doing in the intervening time, and we can work out how far the light has actually travelled. But it does rely on us having some sort of model of how the universe is expanding. So we need to know things like, what is the Hubble constant? The Hubble constant tells us that at the moment, how fast is a galaxy receding from us if it's at a particular distance. If it's at a distance of 1 megaparsec, then it's receding from us at about 70 kilometers per second. That is the value of the Hubble constant at the moment in these rather odd units of kilometers per second per megaparsec velocity for a given distance. But if we know that's what the Hubble constant is now, we can sort of work backwards and figure out what the universe has been doing for the last 14 billion years. We can also do measurements of the cosmic microwave background which tell us something about what the universe was doing in the past. So with the right sort of input, with the right sort of models, we can work out how things have been moving over the last few billions of years. And that's what I've done here. I've thrown some numbers into a calculation to try and work out, for a given redshift, for a given amount that the spectrum has been moved into the red end of the spectrum, what would the distance of the object have been when the light left, distance then in blue? How long has the light been travelling, or how far has the light travelled? If we do the light travel distance in light years, that's the same as how many years has the light been travelling. And then in red, how far is it to the object now that the light has arrived at Earth? So we can measure each of those distances, distance then, distance that the light has travelled, and distance now. And if we put in the numbers for our quasar that we've just photographed at a Z value, at a redshift value of 4.3, then we find we get these particular numbers. So let's just get rid of the background curves and remind ourselves what those numbers mean. So that means when I photographed this quasar, the quasar was about 5 billion light years away when the light was emitted from the quasar. But it's taken 12 billion years for the light to reach us. In other words, the light has travelled a distance of over 12 billion light years because it's taken 12 billion years for the light to reach us. And remember, the age of the universe is about 13.8 billion years. So that value of 12, or 12.4, if we want it a little more accurately, that number is approximately 90% of the age of the universe. In other words, by taking this particular image, we've looked back in time approximately 90% of the way back to the Big Bang. Now, if you were lucky enough to own the Hubble Space Telescope, you could see objects with a higher redshift, and you could look back 95% of the way to the Big Bang, rather than just 90%. That extra 5% costs an awful lot of money. And during those 12 billion years that it's taken for the light to reach us, the universe has continued to expand, and so now the quasar is about 25 billion light years away. Started at 5, and then during 12 billion years, it's now about 25. And if you simply think about these numbers, what is the distance increase during the time it's taken the light to travel? If originally it was about 5 billion light years, and then it was about 25 billion light years, that means the distance to the object, the distance to the quasar, has increased by about 20 billion light years, but it's done it in a time period of only 12 billion years. So that leads to a very interesting conclusion. A quick back-of-the-envelope calculation tells us that during those 12 billion years, the distance has increased by more than 12 billion light years. If speed is distance over time, then the average speed is the average distance covered over the time, 20 billion light years in 12 billion years. That means this object is receding from us, on average, at about 1.6 times the speed of light. It is receding from us faster than light. It has been going faster than light, and it still is going faster than light. Remember those curves I showed earlier? If we have an understanding of how the universe is expanding, then we can work out what its speed was at any given time. If we're talking about light that left at a redshift of 4.3, then we can work out how fast that galaxy was moving at the time, and we can work out what it's been doing during those last 12 billion years. We can work out how fast it's moving now. The average should work out at about 1.6, but it's very interesting to throw these numbers into the calculation and then find that when the light actually left the quasar was receding from us at more than twice the speed of light. It was receding from us at 2.2 times the speed of light. And it's now a little less, but notice that it's not just a straight line from one to the other. What's actually happened is that the recession velocity of this quasar dropped for quite a few billion years. But look what's happened recently. It started accelerating. So you might expect if the universe is expanding, you might expect it to expand quite quickly and then slow down because gravity will be pulling on everything in the universe and presumably slowing the expansion down. Not so. It appears that in the last few billion years it has been accelerating. This is the great mystery behind dark energy. Dark energy is simply the name we give to try and account for the fact that that curve is going up. It doesn't actually add any physics, it's simply saying something is giving the universe a push. Instead of things slowing down as the universe expands, something appears to be pushing and making it expand even faster. A sort of anti-gravity, if you like. And dark energy is the label we give it, but just because we give it a label doesn't mean we understand it any better than we did before we had a name for it. So that's interesting. I note that the average is about 1.6, but it started off faster and it's currently a little bit faster, but for quite a few billion years it was trogging along at a mere 1.5 times the speed of light. But at no point does it actually drop below 1, you notice. Very interesting. What has the light actually done? If we imagine that here we've got a plot of distance from us in billions of light years, and the vertical scale is time, so 0 down here is the Big Bang, and we are sitting here at 13.8 billion years. So that's us here and now, and that's the quasar at a distance of 4.5 or so billion light years from us, back at about 1.5 billion years after the Big Bang. This is 12 billion years ago. That's when the light left the quasar. So if it started off with the quasar at a distance of 4.5 billion light years, you might expect that the light on trying to get to us is going to take that route because, well, no it can't, because that would mean the light would have to travel faster than light, which is by definition an impossibility. So we can't have the light simply go from there to there. Remember that the universe is expanding at something like twice the speed of light at the point at which the light leaves the quasar. So the light cannot follow that dotted line. In fact, what's happening is that the expanding universe, the light is trying to make its way to Earth, but the expanding universe is expanding faster than it can travel, and the light is actually getting dragged backwards. The light starts at something like 4.5 billion years away, billion light years away from us, but for the next few billion years, the light is even further away from us. Even though the light is trying to travel towards us, the expansion of the universe is dragging it backwards. Remember, swimming through a head tide, as it were. You're trying to swim through the water, but the water is moving faster than you are backwards, so you're getting dragged backwards. Or if you like, you're the ant on the rubber band, and the rubber band is being stretched faster than you can walk. So it's really weird, but for something like 2.5 billion years, the light is actually getting dragged backwards before finally the light makes enough headway to start making it towards us. So on a distance from us and time graph, that is what the light actually does. It's weird, but that's what happens when you live in an expanding universe. If the universe wasn't expanding, we wouldn't have any of these complications. If we ask what happens to the quasar itself, we know that light from the quasar follows the green path. During those 12 billion years that it takes the light to get to us, what does the quasar do? Well, remember, the quasar started at about 4.5 billion light years from us, and as time goes by, the quasar simply gets further and further and further and further away until it's, 25 billion light years or so away by the time we get to the here and now. I've shown it as a dotted line simply because it is not actually a straight line. Remember what I showed just a slide or two ago? The actual velocity, the recession velocity of the quasar, actually varies. It starts off fast, then it gets a bit slower, then it gets a bit faster again. So if we plot its position on a distance and time graph, the gradient effectively gives us the speed. So if the speed is changing, that red line ought to be a little bit wiggly. But I couldn't figure out exactly how wiggly to make it, so I just drew it as a straight line with the caveat that it's not perfectly straight. There's actually a little bit of a wiggle in there, determined by the changing velocity of the quasar. If we think of it in terms of the light's journey, it's quite a remarkable journey. We have to go back 12.4 billion years to the origin of the light. So that means the light was emitted by this quasar about 1.4 billion years after the Big Bang. It had already been travelling for something like 8 billion years when the Sun and the Earth were born. So in other words, we're talking about a journey that started long before the Earth ever even existed, or the solar system existed. So for 8 billion years it was travelling through the void, and after 8 billion years or so the Earth was formed in the solar system. The Sun was formed and the solar system was formed and the Earth was formed. And of course the light just trogs on. Life evolved on Earth, the light travels on. Dinosaurs came and went, the light travels on. In the last million years or so of its journey, it arrived at the edge of our Milky Way galaxy. It crossed a few spiral arms, I'm not sure how many it crossed on the way in, and then it would have entered the solar system. In its last few hours, it would have arrived at the Earth. It would have taken just a fraction of a second to travel through the atmosphere. It would have hurtled towards England, dodged a few clouds on the way, entered the lens, and then hit the camera sensor and produced the image that we saw quite a few slides ago. Just 1 pixel in the image, but what a journey. So this is a graphical representation of what I've been saying. There's the main image in the middle. In the bottom left is the camera that I used to take the picture. In the top left is showing you where I pointed it in the constellation of Draco, and in the top right there's a blow up of the central region of the image where the quasar is highlighted by the 2 grey lines there. And a reminder of the stats in the bottom right, a redshift of 4. It's taken more than 12 billion years for the light to get here, and the distance to this object now is a phenomenal 25 billion light years. So to answer the challenge question, is it possible to capture the light from one of these remote objects without a telescope? Yep, you just need a camera and ideally a telephoto lens to make sure that you've got the scale to see the individual quasar. And yes, it is possible for a camera that's not modified for astrophotography to catch what I like to think of as, from this quasar, its ancient light. Thank you all for listening to this short presentation.